Hey guys, welcome back to another RASK math tutorial, and in this tutorial I'm going to be showing you guys how we can find the stationary points of a 3D function. So finding the stationary point of a 2D function, or just on a Cartesian plane, 2D Cartesian plane, is pretty simple. We just differentiate and set when the derivative is equal to 0, and that tells us when the function is got a 0 gradient, so therefore it's stationary. 3D functions are actually a lot simpler than you might think, and essentially we're going to use the same technique but just scaled up. So here you can see I've given a 3D function f of xy is equal to x plus y squared plus x squared. Pretty simple. So yeah, this is the function and we want to find the stationary points, and I think we can see from this graph that the stationary points are somewhere around the origin. Sorry, the stationary point. You can see there's only one stationary point, and it's somewhere around the origin, although I'm not sure if it's exactly at the origin, although it probably is, seeing a symmetry, but yeah. So how would we find this? Well, the basic idea is we differentiate with respect to each of the variables, and then we just solve for when both of those derivatives are equal to 0 in simultaneous equations. So let's bring this function over to here, x plus y squared plus x squared. So if we had a regular function f of x, what we do is we just take df by dx, and that's just going to give us the derivative, and then we just set that equal to 0 and solve for x. That gives us a stationary point. Well, we can do a similar kind of thing here. So we're going to solve first for df by dx, and then solve for df by dy. And since we're taking partial derivatives, or what these are called, we use the delta sign rather than just the d. We use the delta to represent partial derivatives. So we take the partial derivative of x of f with respect to x, and this is just going to be, when we take the partial derivative with respect to x, we just treat y as a constant. So this first part is just going to be using the power rule. It's just going to be 2x plus y. Derivative of the inside part is just 1, and y is just a constant, so we can kind of just leave that there. Plus, of course, we have this 2x from using the power rule over here. And if we just simplify this a little bit, this gives us 4x plus 2y. And we're solving for when df by dx is equal to 0. Essentially just solving for this equation, 4x plus 2y equals 0, or 2x plus y equals 0. So here's our first equation. It's 2x plus y equals 0. Whenever the points satisfy this condition, we're going to have df by dx equal to 0, or it's going to be stationary in the x-plane. Okay, so now let's take this derivative with respect to y. So we have df by dy. As y changes, how does f, the function, change? Well, same kind of thing here. So now we take this part and we treat x as a constant, so it gives us the same term, since the derivative of the inside part is still going to be 1. And then this plus x squared, well, since x is a constant, that just disappears, since we're differentiating with respect to y. This x squared is just a constant, and constants differentiate to 0. So ultimately, this is our derivative with respect to y. And if we're setting this equal to 0, this gives us our second equation as just x plus y is equal to 0. And divide everything by 2. Okay, so here's the second equation. Now we have two equations, two unknowns. We can simply just solve for the points, and if you just, let's just write this out neatly. 2x plus y equals 0 and x plus y equals 0. It's fairly obvious that the solution to this simultaneous equation is just going to be x equals 0 and y equals 0. And that confirms our initial suspicion that the origin was the stationary point. So this tells us 0, 0 is a stationary point. And the great thing about this method is it can actually be generalized to any n-dimensional function, because we just take the derivative to each of the with respect to each of variables. An n-dimensional function has n variables, so that's going to give us n partial derivatives. We set each of them equal to 0, so now that's going to give us n equations to solve. So we have n equations with n unknowns, so we can always solve for a stationary point at least, and find all the stationary points. So you can see how this method can be generalized to higher order functions and find the stationary points of all functions. But it starts to get a bit weird, because what is the stationary point of like a 5-dimensional function? If you know about machine learning, you might know that we can use that to minimize algorithms, cost algorithms, things like that. But yeah, that's for a later video. And in this video, I just showed you guys how we can work out the stationary points of a 3D function. So yeah, thanks for watching, and I'll see you guys in a future tutorial. Bye.